Okay, so this is going to be our very first video for Calc BC, and we are starting off in the of calculus. So as an introduction, we know that there are many rates of change that we talk about. How fast we drive, how our money grows over time, how population changes, unemployment rates. You hear about it in the news all the time. We always talk about rates, how things are changing. So what we're looking at is how one variable changes in terms of another. So we're looking at functions, y equal f of x. So we're going to start with the most obvious one, which is velocity. So velocity, for now, is going to be an object that travels in a straight line. So our average velocity is over a given time interval is the ratio of the change in position, sometimes it's called a displacement or net change, to the elapsed time period. And we're going to use for position most of the time, unless it's otherwise noted, s of t, which is used from physics, that comes from. So our average velocity is defined as the change in position over the change in time. And if we want to look at this in terms of a time change, so if we start at time 0 and we travel to time t1 or any time t0, we are going to have s of t1 minus s of t0 all divided by t1 minus t0. And that, of course, is our slope formula. And we're going to build on that. Okay, so most of the time, though, if you talk to someone about their velocity, we're talking about the instantaneous velocity, which means the speed and direction of an object at one instant in time, at one particular moment. And it's not always going to be exactly the same as the average velocity. So why can we not use this ratio for instantaneous velocity? Why does this become a problem? So I'll give you a second to think about that. And the reason for that is that our time interval t1 minus t0 is going to equal 0, and we cannot divide by 0. So we have to come up with a different way of handling this. And so we're introducing the concept here in this section, and later on we're going to come up with some more direct ways to do this. Okay, so that leads us to the next question, which is, how can you estimate an instantaneous velocity? And so our answer to that is going to be, we want to make the time interval very small. So the distance between t1 and t0 is as small as possible. So it seems like the time didn't even pass. Like in an instant, a split of a second, like 0.001, a hundredth of a second, a thousandth of a second, something like that. That's what we try to do. Okay, so that's going to lead into our first example here. Let me just note here, as I said, the average velocity over a very small time interval is very, very close to the instantaneous velocity. Okay. So here's our problem. If you climb to the top of the Tower of Pisa, and I have a little picture there, and drop a coin to the ground, estimate the instantaneous velocity at 0.7 seconds, 7/10 of a second. Use Galileo's formula, s of t equals 16t squared, to compute the average velocity in feet per second over the time intervals listed in the table below. And then we're supposed to say, what is our instantaneous rate of change estimate at that time? And we're going to be using that abbreviation for instantaneous rate of change, the IROC. Okay, so I've laid out the time intervals for you here, and you can see in the first interval it's a hundredth of a second, and then it's 0.005, so it's 5 thousandths of a second, and then 1,000. We're getting smaller and smaller and smaller in our time interval, so that by the end we won't even, it's probably as fast as the blink of an eye. Okay, so filling in this table, what we have is these values are 22.48, and then we have 22.402. And I'm going to tell you right now that on the AP test, they expect you to keep 3 decimal points rounded or truncated. So I'm going to stick to that when I write my answers, even if there are more decimal points available, just to get us in the habit of writing them in that fashion. Okay, so how did I get those numbers? So here's how I got them. If I look over here at the first one, what I did was, so that's for the first one that I filled in right here. I have to get used to pressing that. Right here, the first one I filled in. What I did was I calculated the value when I substitute in 0.705 here, and then subtracted from it the value at 0.7 seconds, and then I divided it by the time interval here. And I did that for each one of them to get these values in the table here. Okay, so looking at the last value, this can be our estimate for our instantaneous rate of change. So we can write the coin, you want to write good answers. The coin is falling at a rate of about 22.400 feet per second at t equal to 0.7 seconds. You want to make sure that you emphasize at what time, because the instantaneous rate is going to be different at different times. Okay, so that's our introduction to this. So we're going to look more closely at how we study rate of change in calculus. So we got our time intervals to go smaller and smaller in the first example. So the key to that is the idea that the average rate of change converges to the instantaneous velocity. Or, in other words, as we've used last year, the instantaneous velocity is the limit of the average velocity. And we'll talk more about that part of the definition in the next section. So right now we're just introducing the concept. Okay, so let's look at a graphical representation of our velocity. So here's a curve, and this is time over distance. And what we want to find, our average rate of change, our AROC, is defined as the total distance traveled divided by the elapsed time period t. So we have this little ratio that we should be very familiar with analytically. That's our slope formula, delta d over delta t. Graphically, what we have is we have the slope of the secant line. So if we were to draw a line, here's my line, it didn't show up right away, through those 2 points, the slope of that line is going to be the average rate of change. Okay, so what we can do is use the value of these 2 points to estimate the average velocity. So the first point is at 1,3, and the second point is at 4,4. So using that, we're going to do the slope of the secant line. is equal to the change in d over the change in t, or y2 minus y1 over x2 minus x1. So that's going to be 4 minus 3 over 4 minus 1, and we get 1/3. So that's the slope of that secant line, or the average rate of change between those 2 points. Now, it is going to change as we change one or both of the points, so please keep that in mind. Okay, so the other concept that we have is the instantaneous rate of speed, or the IROC, the instantaneous rate of change. So this is the speed at a specific instant in time, and it is the limit of the average rate of change. And like I said earlier, we're going to get into that more in the next section. Okay, so graphically, instead of having 2 points on the graph, we are looking specifically at one point, at point C. And if a line touches a curve at one point, it's tangent to that curve, so we're looking at the tangent line. And if you notice, it says we need calculus to determine this instantaneous speed. And I know what you're saying, well, this is calculus, we should be learning that, but we will. So as I said, this is just an introduction. So what I want to show you is what the tangent line looks like. It hits the curve at one point. Okay, that is a terrible line. Let me try that again. It's so much easier to do it on paper than it is on the screen. Oh, that one's pretty good. I like that one. Okay, so this is going to be our tangent line. And what we want is the slope of that line. I know what you're thinking. We only have one point that touches the curve, but we do have another point over here, which should be that point right there, which is 5, 6. If I drew a better line, it would be much easier to see. And 2, 4 is where point C is. So we can estimate the instantaneous velocity by taking the slope of that tangent line. So the slope of our tangent line is going to be our instantaneous rate of change, which is going to be 6 minus 4 over 5 minus 2. And we get 2/3. Okay, so let's do another example related to this. So now we're at spin class, and we're looking at our heart rate. So even if you haven't taken a spin class, you've probably seen it on TV or something. Your heart rate goes up really, really fast, and it's really high when you're done. So your heart rate is going to decrease quickly as time passes. So we're going to let the function h of t represent our heart rate, and we're supposed to write an expression for the rate of change of your heart rate over the period from t equals 0 to t equals 90 seconds after we've stopped exercising. So we don't know exactly how we're representing our h of t, but we can write an expression. So what we're going to know is that we want to find the value after 90 seconds of our heart rate and the value right after we get off the spin bike, like that. And then we're going to see the change in the amount of time, which in this case is 90 because we're starting from time 0. So the expression we're looking at is h of 90 minus h of 0 over 90. Now I'm going to stop this video here, and in the next video I am going to do 2 more examples to finish out this section.